All right. How's everybody doing? So while we're getting set up and waiting, anybody have any questions about anything? Homeworks, controls, etc. Cool. Um, uh, General announcement. Homework is due Wednesday night. I sent a Slack message to clarify that. So just like last time, and I think we're going to try to keep the cadence now the same for the rest of the class. So homework's going to be due Wednesday midnight, say, and then the next homework will go out Thursday and be due 2 weeks Wednesday. The other announcement related to homework is that I added 4 more late days to your late day budget. So there's a total of 6 for like the whole class. I think we're gonna have 5 homeworks, so it works out to roughly, like a day per homework plus a floater day, I guess. And I'd ask, please, yeah, just for the to make the grading sort of and posting solutions and everything go smoother. Be ideally we'd use max 2 per assignment. So like basically by by Friday night. Uh, if you have some kind of issue where you can't do, for whatever reason, if there's circumstances, like that's cool. Just let us know. Everybody has things going on. It's understandable. It's not a big deal. We're all pretending to be adults and stuff. It's a grad class, so yeah, we'll be accommodating. But just in general, yeah, just let us know you got some kind of issue. Okay, so everybody good otherwise?
When is
All right.
the group survey due again?
Oh, the project proposal.
Too?
Yeah, I was gonna say, yeah, like same deal, like Friday or Wednesday night with the homework submission time. But yeah, like that's kind of flexible. I mean, I would appreciate it. The intention there is I'm gonna read them and like get back to you guys. A lot of you have talked to me already during office hours about your project ideas, which are, and most of them have been really cool. So that's great. But yeah, it's basically so I can get a read on what you're thinking about and maybe give you some pointers and like steer you into a more tractable direction maybe, or give you some references to check out, that kind of thing. So it's intended to help you guys get started and kind of force you to think about it. I mean, let's say, yeah, so nominally Wednesday night, let's say I won't have time to really look at them until Friday, probably. So let's say for sure by Friday morning, because that's when I will have time to look at them. So if you want me to look at them and give you feedback and whatever, Friday morning is probably when I have time on my calendar to do it. So by Friday morning for that would be ideal. Does that make sense, everybody? And if anyone has questions about that, I'll have more office hours Friday, probably like I did this week, this past week, to talk about project stuff. And I'd like to actually get every group at least to come through those, to have a time to chat about that stuff, just to make sure everyone's got a solid project idea and is sort of getting started thinking about it. Okay, so here goes. Tablet. Excellent. All right, so that seems to be working. Cool. All right, so last time we talked about convex MPC. And yeah, that's like a super, widespread technique that's being used all over modern robotics, from like autonomous driving to SpaceX landing rockets, NASA landing on Mars, to all the advanced quadrupeds, probably Boston Dynamics, almost every like modern, sort of that's kind of the go-to modern control technique, I would say, for like online tracking, control, and stabilization kind of stuff. So really good to know about and check out. And you guys are implementing it for the sort of simplified 2D rocket problem on the homework. So you'll get a taste of what that looks like. So today, what we're gonna kind of now get into like what I think of as the fun stuff, like what what kind of really originally got me into these techniques. We're going to talk about nonlinear trad-op today, and just getting started with it. And in particular, we're going to talk about an algorithm, or I should say more like a family of algorithms or class of algorithms called differential dynamic programming. I'll put AKA iterative LQR. They're basically the same thing. There's some dubious, reinventing of things in here, depending on how cynical you are. The original differential dynamic programming algorithm was by Jacobson and Main in the late 60s. And then it was reinvented in 2004 under the name iterative LQR with no citation of the prior, 30 years of work on these things. But, that's all right. Okay, so that's what we're talking about today, and sort of digging into this nonlinear stuff, the more general setting. So first I want to just write down the, I'll start abbreviating so I can write faster. So again, just to lay out the problem we're going to try solving, the same sort of things we've been looking at, but here I just want to point out a couple features. So our minimize J, which is this sum from k equals 1 to n minus 1 of a one-step cost or stage cost that can be time varying, and then a terminal cost. And subject to now general nonlinear dynamics. And yeah, if you want, that can be time varying too. And then also now I'm going to use kind of the abstract notation, xk in some set and uk in some set. So these can be pretty much any, all right, so let's do some notes. These can be, so this is dynamics constraints. Nonlinear in general. Now we're finally going to do nonlinear stuff. These cost terms also can be general nonlinear non-convex. Although I would say in probably 80–90% of applications, we still end up with quadratic looking cost functions in most control applications. So those are often still convex, but we have these nonlinear dynamics to contend with. And then these other constraints, these can also be totally general. So these can be generally, nonlinear, non-convex. They can be equalities or inequalities. Pretty much anything's fair game. Common things, right, are torque limits, thrust limits, obstacle avoidance constraints, which are almost always non-convex. Let's see, there's heating constraints on entry vehicles is one that's come up. Yeah, pretty much anything is kind of fair game here. Okay, and then kind of a couple notes are that usually we assume that costs are C2, meaning differentiable at least twice, and we have access to continuous second derivatives. And that all the constraint functions, including the dynamics or other constraints, are assumed to be C1. So this is continuous first derivatives. And these assumptions are there because of the solvers, right? We're using these kind of Newton method kind of solvers, and typically we require, in order to make those things work, Hessians of the cost function and Jacobians of all the constraints, right? So these are just like the bare bones things we need to write down a KKT system, right? So there are, by the way, there are a lot of robotics applications where those assumptions are violated. Those end up being hard problems. One of the biggest ones that's super common is anything having to do with intermittent contact. So like locomotion kind of stuff where you have impacts and friction. There you lose these smoothness conditions and you have to sort of think outside the box a lot. And we'll talk about that. Okay, so any questions about this assumptions? So this is the problem we're going to attack. Today, we're going to focus on no additional state or input constraints. And we're going to sort of dig into this differential dynamic programming thing. So let's do that. Okay, so actually, I'm curious, who's heard of this, seen it before? We do the raising of your hands kind of deal. A handful. Okay, cool. Not too many though. All right, so here's what this is. So this is a nonlinear trajectory optimization method based on approximate dynamic programming. So it fits into this whole dynamic programming conversation we've been having. And this is kind of I think this is a really interesting algorithm for a bunch of reasons. So one is it sort of fits into a bunch of the classical category bins that people try to classify these trajectory optimization algorithms into. So the gist of it, the basic high level idea is that we're going to use second order Taylor expansions Taylor approximations of basically everything, of all the functions in this problem. So in particular, though, where it shows up the most is basically what we're going to do is second order expansion of the cost to go function. And we're just going to kind of do whatever we have to do to maintain that second order Taylor expansion of the cost to go in the backward dynamic programming pass. And that's going to allow us to compute kind of improvement steps, basically like Newton steps. To both our feed forward U trajectory as well as a local feedback policy. So that's the high level idea. There's a bunch of ways to think about this, like I said. One way that I kind of like to think about it is basically a mashup of Newton's method with dynamic programming. It's like you took dynamic programming and like did Newton and like bolted Newton's method on top of dynamic programming, kind of. Okay, so just a couple notes about this. This is a fairly popular technique in robotics. One of the reasons is that it can have extremely fast local convergence. It's basically a full second order kind of Newton style method, and it's taking advantage of all this problem structure from the trajectory optimization problem in this dynamic programming setup. So it's sort of like taking advantage of all the problem structure and is extremely efficient. And because of the second order approximations, it's kind of a full Newton thing. It can be very fast. So I would say DDP is considered one of the fastest, probably trajectory optimization algorithms, though it has some limitations that we'll get into. Okay, cool. So that's kind of the background stuff. Now we're going to get into it. So here we go. So first we're going to have the cost to go Taylor expansion. So we're going to take this up to second order. And so that's going to look like VK of X plus delta X is approximately VK of X plus a linear term. So this is like the gradient term, right? And then a Hessian term. So we're going to use little p for the gradient and big P for the Hessian. I'll just make that more explicit. So this guy is del X of, oh yeah, so then to like sort of bootstrap this right at the end, we have little pn equals the gradient of the terminal cost, and big P at the last time step equals the Hessian of the terminal cost. Okay, so that's how we start. And the other thing I'm going to write down here is it ends up just being convenient. This derivation is sort of involved and a little heavy on the notation. So we're going to make some notational sort of definitions to make life easier. And particularly, this is a little easier to do in terms of the action value function, the Q function. So we're going to also, same story. We're going to also Taylor expand that. So this guy is S of X plus delta X, U plus delta U is approximately, so we're going to write these guys as, so it's the nominal sort of X U value plus a gradient term. We're going to use G's for this guy. So this is GX, GU, so the gradient with respect to X and U, right, times delta X, delta U, plus the Hessian term. So same kind of deal, delta X, delta U, transpose, and we're going to call the Hessian blocks GXX, GXU, GUX, GUU. This is just for making our notational wise easier, so it doesn't get too crazy. All right, so that's what we've got. We've got these second order expansions of all these things. Now what we're going to do is just write down the Bellman equation for a given time step. So we already kind of know the DP formula, right? We start at the time step n, we got the recipe for setting that up, and we go backwards with this recursion. So all we really need to do is write down one step of that Bellman recursion and derive kind of the update rules for deriving sort of PK in terms of PK plus 1, right? And it's going to look a lot like LQR, just with a bunch of extra terms. Let's start the page. Okay, so here's this thing. So we've got V n, or yeah, I guess we'll go n minus 1 of X plus delta X equals min over U of, we're going to now plug in the action value thing. So S n minus 1 of X U, min over delta U, plus, and this is just exactly what I wrote down before. We're just going to plug this in, and there's a lot of sort of notation floating around. So I'm not going to put the time indices on this stuff right now because it's going to be too terrible to fit everything in. So we'll leave off the time indices, but they're all going to be sort of, it should be pretty obvious what we're writing down. Okay, so X U plus G sub X, the gradient with respect to X, times delta X, plus gradient with respect to U, delta U, plus, yeah, it's the obvious thing. No surprises here. Let's see. on there. Plus, then we've got these other terms that the sort of mixed terms, and we can kind of write them both in one shot. GXU. Cool. So I can write both of these. I guess I might as well. Okay, so these last two terms, by the way, are the same. So usually you'll leave one out and leave off a 1/2. Can anyone tell me why those last two terms are the same?
Because the Hessian is symmetric.
Yeah, that's right. Because we're assuming these functions are nice, mixed partials are always going to be assumed to be the same, right? So if I differentiate with respect to x and then with respect to u, or if I differentiate with respect to u first, then with respect to x, I get the same answer. So those off-diagonal blocks in the Hessian have to be just each other's transpose. They got to be equal. So we can make a note of that. Cool. So, right. Okay, cool. So we're going to do this. We're going to then just explicitly take the derivative of this thing with respect to u and set it equal to 0 in the usual way. So let's do that. Partial this thing with respect to u equals GU plus GUU times delta u. Or I should say, sorry, this is partial respect to delta u. We're minimizing respect to delta u. It's a lot of bookkeeping going on here. Plus GUX delta x equals 0. And then from there, we can solve for delta u. So delta u n minus 1 here equals minus GUU inverse GU minus GUU inverse GUX delta x. All right, so this is very similar to LQR with one difference, basically. So this term is actually exactly the same as the thing you get in the Riccati equation. If you plug everything in, and it's a linear feedback term on the delta x's. So we're going to call this guy k, and here it's n minus 1 as the time step. And that's coming from the Hessian terms, right? That's coming from the quadratic terms in this cost to go or action value function. And that's same as LQR. We also have this new term that we didn't have in the LQR derivation. We're going to call this guy D. This is a feed forward term, right? It's a constant term, a constant adjustment to the U's that we did not have in LQR. And that's coming from the linear term or the gradient term in the cost to go or action value function. So what's going on here, right? One way to think about this is in the standard LQR setting, we're trying to do tracking control or stabilization of a point. And kind of the idea there is the cost to go function is purely quadratic. It has a distinct minimum at the origin, say, and that's because we already know where we want to be. We already know what the trajectory is that we want to track or the equilibrium point we want to be at, and that's it. So it's only the linear feedback term that's stabilizing the already known trajectory. In this context, we don't know what the trajectory we want to stabilize is yet. So the way to think about this is there's a gradient term here that's sort of nudging us downhill in the cost function. And so that's giving us a feed forward update to the controls that's nudging us towards a better trajectory. Whereas you have now also this feedback term that's like then trying to track that trajectory or stabilize that trajectory. I don't know if that made any sense. Hopefully that's sort of getting at a little bit of what's going on. Okay, and then the next step here is we're gonna just take that. So I guess I can write this down now in like, so, equals, we'll write it as minus D n minus 1 minus K n minus 1 delta x. And we're going to plug this back into, unsurprisingly, into that action value function to recover Vn minus 1, right? Just like we did with LQR, it just has more messy terms in it. Oops. And again, what we're getting when we do that, we're plugging in delta U to get, again, this Taylor, second order Taylor expansion in Vn. So we're plugging in the delta U's to get rid of those, but we're going to get now this like Vn minus 1 of x plus delta x, like the Taylor expansion of that guy in delta x. So when we do that, we get Vn minus 1 of x plus delta x equals, or approximately, right? We're doing this approximate thing the whole way back. The nominal value that we had before, it's just a constant, right? Then we're going to pick up a bunch of, so we got some stuff is already okay. All the x terms basically don't change, right? But now we get, for example, GU, we're going to plug this thing in here. So we're going to get minus D minus K delta X. Then we've got the quadratic term in X, that's fine. We got the quadratic term in U, we just get 2 of these things. Half out front. And then what else we get? We get then we get the sort of cross terms, those delta X transpose G X U Dn minus 1. And the other cross term. Okay, that's the whole thing. Ugh. And then what we're going to do from here is we're just going to collect terms and pull out the Hessian and gradient of this guy so that we can write down the recursion for Pn minus 1. So here's just all I'm going to do now is pull out all the Hessian blocks, right? All the squared terms, all those matrices that are in here where they're smushed between 2 delta x's. So we get this thing. Okay, so there's big P, the Hessian, and then little p, the gradient, is going to end up being Px minus. Okay, I think that's the whole thing. So this, let's see, this gets a box. And these guys get a box. Okay, that's the whole thing. So now we start at the end. We got the PNs, right, big and little, in terms of the terminal cost. And then once we've got those, we've got a recipe now for computing a delta U, where we get a feed forward correction to U, the nominal U plus a feedback term on delta X. And then we plug that back in to the action value function, and we get these P's for the next time step. We can kind of set ourselves up and do a backward pass, just like LQR. You basically, it looks a lot like LQR, but it has a bunch of extra terms. It has a bunch of like gradient terms and a feed forward term in addition to the feedback term. So any questions about this? Everyone feel okay about this? So what we got to do next is, so I wrote this all in terms of just these generic action value function expansions, like these G's basically. We didn't derive the G's though. So right now you don't know how to actually plug the G's into these equations. We have to derive the G's in terms of like dynamics and cost function expansions and all that kind of stuff that we know. That turns out to be slightly messy. So what I'm gonna do is teach you guys some math tricks that are not super, I would say, common or well appreciated, but are extremely useful in my experience. So basically what's going to happen here, and the reason we're taking this little diversion, is that inside these G's, you end up having to do some tensor math. You end up needing like second derivatives of the dynamics, which end up being third rank tensors. And that's sort of annoying and a pain to deal with. And then a lot of derivations, they kind of gloss over the details of that. I'm going to show you how to do it in a way that I think makes sense to me at least, and is nice, but is sort of not super standard. I've used these tricks a ton though, and I find them super useful. So I figured it's my class. You can I think it's useful. So here we go. So this is a set of tricks that goes by the general name matrix calculus, rather than, as opposed to tensor calculus. That is what it's in sort of contrast to. So here's kind of the idea. And actually, I'd be super curious if anyone's used these tricks before. So definitely speak up if you've seen these before. It took me, I didn't learn these till like I was a postdoc, and had to suffer through doing a bunch of tensor math and then stumbled upon these tricks. Okay, so if we have some f from Rn, say to Rn, we want to let's look at the second order Taylor expansion. Okay, so the stuff we've been doing, if m equals 1, i.e. The output of the function is a scalar, then we kind of know how to do this, right? It's a standard kind of thing we're used to, where we're going to get a gradient. And this guy will be 1 by n. And then we're going to get a Hessian matrix. And this Hessian matrix is going to be n by n, right? X is n dimensional, right? Okay, so that's nice. This is how we do cost functions. We've been doing this the whole time, right? This is what we need in Newton's method. But what if n is bigger than 1, which is usually the case when we're talking about dynamics functions? That's the situation, right? So in that case, we're going to get f of x plus f partial x delta x. So this is fine. We do this all the time. This is now a Jacobian matrix that's m by n. What about the second derivative? So I can write this a bunch of ways. I'll write it for now like this. So if I have, say I already have, if I compute partial f partial x times delta x, that's the Jacobian term that I just had. I want to take another derivative of this. So I can sort of nest the derivatives and then multiply that by a delta x. So that sort of gets at it. And maybe this sort of way of writing it is workable for an auto-diffing toolbox, where you can write these. If you can nest automatic differentiation calls, you could write something like this down, right? But this is sort of ugly and sort of doesn't actually allow you to explicitly write down that second derivative of f. So I will just write ugly. So how do we actually write that last thing down? I'm curious, what have people seen before? If you've had to ever do this, how would you write that thing, that partial f, d squared f dx squared for a vector valued function like this? And there's 1 d squared f dx squared is what's called a third rank tensor. You can think of this as basically like a 3D matrix in some sense.
Is it going to be a sum of derivatives? You'll have to sum over something.
Yeah, you could do that. That's sort of messy and involves writing down for loops and holding on to a whole bunch of matrices, and it's sort of ugly and also can lead to bugs. The tricky part with these tensor things is when I'm doing something like this, right? You can think of it like a 3D matrix. And it's sort of in the same way where if I'm multiplying a matrix by a vector to get a vector output, I can multiply it two ways, right? I can do A times X, or I can do A transpose times X, which is sort of the same thing as like X transpose times A. So think of it as like for a matrix, there's two ways I can multiply it by a vector, right? There's sort of like two sides to it that I can multiply on, and I get, in general, different answers. For a third rank tensor, there's three ways I can multiply it by a vector. And in general, we'll get three different answers. So keeping track of which dimension you're multiplying along ends up being messy and tricky. And physicists have a good system for doing this, or a system, depending, goodness is up for debate, called Einstein summation notation or tensor notation, where you explicitly keep track of how many indices there are, which is like the number of dimensions you can multiply along on these things. And it's sort of, it works, but there's kind of another way that I'm going to show you. Basically, we need some more notation. So you kind of keep track of that. Which dimensions we're multiplying. Okay, so that's what we're after. So here's the tricks. I'm super curious if anyone's seen these tricks before. So first one is the Kronecker product. Anyone heard of this? Show of hands. Couple, okay. To you, Kronecker product. So this guy is, if I have two matrices, A and B, it's written usually like this with this, it's O times in LaTeX. So let's say, I don't know, A is L by M, and B is N by P. It can be any dimension. Then the Kronecker product is I take each element of A, so like A11, and multiply it by the full matrix B. So it's something like this. And I just keep doing this. So this Kronecker product, this matrix, the output will be Ln by MP. It's sort of grows in size. It's like the product of the dimensions, right? So the idea is, again, multiply each element of A by B. Okay, so far so good. And there's a sense in which basically what that matrix is, you can think of that matrix as like a flattened version of a tensor. That's kind of really what it is. So if I have this 3D matrix tensor thing, really what this thing is I'm like taking all that third dimension and just flattening it out into a standard matrix. Okay, so the other trick we need is the vec or vectorization operator. So this thing is, if I have a matrix A, if I look at its columns, so AM for a L by M, then vec of A is just stack the columns from the matrix. So this is dimension LM by 1. Okay, so that makes sense to people. These are simple ideas. So now we're going to put these together. And the magic, this is sort of the magic identity that makes a lot of this stuff work. I've heard this called the Vec trick. I don't know if it has a real name. That's what I call it. So here's this identity that's magic. If you have three matrices, A times B times C, and I take the Vec of that product of the three matrices, it's equal to C transpose Kronecker A times Vec of B. So there are some sort of clear, generalizations of this. Basically, I can take this and I can plug an identity in for any of these that I want to. So that lets me get things like Vec of just AB, say, equals B transpose Kronecker I, where I is identity, times Vec of A, or I cron A times Vec of B. Okay, so some of these, it's pretty clear what's going on, right? So basically, like the last one's the easiest to see. If I imagine the matrix multiplication of A times B, what's going on there is I'm sort of taking the matrix A times each column of B is what that matrix multiplication looks like, right, intuitively. So if I stack the columns of B, I just need to multiply each one of those columns by an A. And this I cron A is basically taking A and just making a giant matrix with block diagonal copies of A. So it produces that exact result where I just take a copy of A times each column of B, right? So that sort of intuitively makes sense. The more general version is a little trickier, but to show, but it's not hard to show. Basically, you can write these things down like column-wise or row-wise and then like show that this works out. Okay, so where are we going with this? Hopefully this made sense. So what this Vec trick allows you to do is differentiate matrix expressions. And in particular, the things we're going to use are, so if we need to differentiate a matrix, say, with respect to a vector argument. So say we have, like, a good example of this is a mass matrix from like dynamics, where it's M of Q, say, where Q is the configuration for people who know dynamics. Let's say I want partial M, partial Q, which actually shows up in a bunch of applications. So what we're going to do is vectorize the matrix first. So what we're going to do is, so let's say we have A of X, where A is a function of X. I want partial A, partial X. We're, by convention, anytime there's a matrix that we're diffing, it's going to mean partial Vec of A, partial X. Okay, so the really awesome thing about this whole setup is the chain rule still works. So if you kind of follow the rules and you make gradients, row vectors, and all the usual stuff that makes the chain rule still work when you do calculus on vectors and matrices, this works with the chain rule. So you can chain rule like kind of complicated, nasty expressions involving matrices now. And just to kind of be clear about this thing, right? So A was L by M. So Vec of A is LM. So this thing is LM by M, right? So it's I vectorize A. So A is just stacked in one big column vector, and then I take its derivative with respect to X, which has dimension N. So it's sort of, I multiply it on the right by a delta X, right, to get the change in A. So that's what those dimensions look like. Okay, any questions about this? Okay, so we'll keep trucking. So now back to the Taylor expansion thing. So if I go kind of back to my Taylor expansion I was trying to do. So I have now f of x plus delta x is f of x plus Jacobian of f respect to x times delta x. And if I now play this game, what I'm going to do now is diff this again, right? So, and then I want to multiply it by 2 delta x's. So I'll write this out. We can talk about how you do it. It looks like this. Where this thing is implicitly is actually partial vec of the Jacobian with respect to x. And this thing is mn by n. Okay, is it clear how we got this? So I think it might be easier to see if I call this thing. So if this thing is our A matrix, think about it that way for dynamics, then this expression over here is going to be 1/2 delta x transpose cron I times partial A partial x times delta x. And it really comes from diffing the expression in the middle, right? So this thing, I pretend this thing is, I want to diff with respect to, I want to diff partial f partial x with respect to x. So I pretend there's an identity on the left-hand side. This really looks like this, right? And then it's our ABC formula. So I do partial x, I do delta x transpose cron I, right? And then I can pull out the A and I can do partial A partial x. Does that make sense, everybody, how I got that? So this becomes, delta x transpose cron I vec A. And then I can take partial vec A partial x. That's how I got that. Everyone cool with this? Okay. So this is kind of it. So with these simple tricks, like these 2 tricks, basically, you can do basically all of tensor calculus with like normal matrices. The reason this is super nice, it plays very nice with NumPy and MATLAB and Julia matrix math. In particular, most of these matrices are super sparse. You get a lot of these Kronecker, like things Kronecker producted with I, where it's just like block diagonal stuff and things like this. And all of those, if you set them up in MATLAB or Julia or NumPy, they kind of automatically stay as sparse matrix types, and it ends up being quite fast and computationally efficient to do it this way. One other note. Sometimes we need to diff through a transpose, which we do in the DDP derivations. So I'll show you that real quick. So if this looks, so to say we have partial x of some A of x transpose B instead of just A times B, this is going to be B transpose cron I times vec of A transpose, but we want to take the derivative of A, not with respect to A transpose. So we're going to stick this other matrix in here, I'll call it T times partial A partial x. So this T thing is called the commutator matrix. And it's just a matrix that turns, so it's defined so that T vec A equals vec of A transpose. Just takes the vectorized A and permutes it so that it's the vectorized version of A transpose. So it's a linear operator. It's literally just a permutation, right? So that's pretty easy. So I think that's it. Okay, any questions about these tricks? They're nice tricks.
Speaking of whether we have seen this before, I kind of remember doing something similar when we implemented the convolutional neural network, because there as well you end up with like 3rd or 4th dimensional tensors.
Yeah, okay.
So yeah, but not sure if it's the same thing.
It probably is. If there were Kronecker products and vectorization tricks going on, it was probably the same stuff.
Yeah.
There is sort of a fully, this set of tricks is like fully general and like expressive enough to do all of tensor calculus. And like, so anything you ever need to do with higher ranked tensors, you can actually do this way.
Gotcha.
And it's very nice for just like implementing things quickly with existing matrix toolboxes and stuff. Okay, so now that we have that, and yeah, like I said, it's not really standard. And I think it's like, I've found it extremely useful. Like I use this stuff all the time. Okay, so now we're gonna go back and use these tricks to write down the real deal action value function derivatives. This is a pet peeve of mine. Like all the papers on this, they kind of write this like very generic-y looking second derivative of f term with some like, you know, tensor multiplication symbol, but that doesn't actually tell you what to do. Like you can't code that up because it doesn't tell you which axes of the tensor to multiply on. And it's sort of not legit. So here's the legit version. Okay, so we have, this is our action value function at time k. It's our one-step cost plus our cost to go with the dynamics inside, right? So that's it. Now I just need to diff through this. It's just chain rule, and I'm going to use the tricks we just used to write down the second derivatives. So, okay, first off, let's do the first derivatives since we know how to do those. So partial s partial x is just going to be partial L partial x plus partial v times partial f partial x. Just chain ruling, right? And so some annotations here. This thing is, I mean, this is just grad v, that's obvious. This thing is a from our sort of dynamics, right? Okay, so I can take this, and if I kind of transpose it and clean that up a bit, gx, the expanded, you know, from our previous derivation is going to be grad L respect to x plus a transpose grad v of x. So this ends up being just grad x of L plus a transpose little p k plus 1, because we defined grad of v to be little p before, right? Okay, so this gets a box. Then we can do the other one, partial s, partial u. Unsurprisingly, same kind of stuff. Oops. Use, oh no, this is still x. Use a function only of x. Partial f, partial u. Chain rule. And then this guy is b from our dynamics. And if I kind of transpose it and clean it up, just like the other one, I get gu equals grad respect to u of L plus b transpose grad v evaluated x phenomenal. So this is going to be just grad x of L plus b transpose p k plus 1. And if I put the indices, I should put the indices. These are k, bk's, right, and ak's. So they're at the current time step, the p is at the next time step. Okay, so that's pretty good. We didn't need tricks for that. The next part is the tricky part that needs like tensor craziness. So I'm gonna just write these down. We can talk about them. So let's do gxx first.
Sorry, maybe a stupid question, but if v is a function of f, why do you have partial of v with respect to x and not to f?
Okay, we can write it that way. I mean, it's v of x, right? It's just grad v, whatever you want to call it. So I suppose, yeah, it is a little ambiguous. Usually we talk about v of x, like v being a function of x, but yeah, that's valid. We can write it that way. You like that? Okay, that's fine with me. Yeah. Okay, let's keep trucking. So now what we need to do for this gxx is basically just diff the gx that we just wrote down with respect to x one more time. So this guy is the Hessian of the cost, one-step cost with respect to x. So del squared xx plus, now what I'm going to get here, I'm diffing A transpose grad V, right? So I'm going to get some chain rule stuff here. The first term is just going to be A transpose grad V is going to turn into the Hessian of V. So del squared V k plus 1. And then I have to take another derivative of that thing with respect to x. So I get another A on the other side, right? So I diff grad V of x, or grad V of f of x with respect to x. I get derivative of grad V is Hessian V chain ruled with derivative of f of x with respect to x, which is A. So that clear? So that's how I get this term. Then the next term is the nasty one. So this next term is, remember, A is also a function of x, right? A is partial f partial x. So now what I have to do is use the tricks that we just talked about to take that derivative in this. And I'm doing like product rule, right? Okay, so that's the first term. The next term is going to be, I'm going to use my convex tricks. I'm going to take grad V. I'm going to like pretend there's an identity on the left. I want to diff with respect to A. So I put A in the middle, my trick. And I'm going to take grad V, which equals P. So maybe I'll just put P in there. So that's PK plus 1 transpose con I. And now it's just partial. It's A transpose. So I need my commutator matrix. And then it's just partial A partial X. Okay. Clear? Questions about that? It's just a bunch of chain rule. It's not that terrible. And now you actually have the legit recipe for computing this. And partial A partial X, again, you can auto diff that, right? If I write down a function that auto diffs f of x with respect to x once, that spits out A, I just write that function down. I write down now another function that just compute that basically does vec of A and then auto diffs that, right? So it's super clean. You can easily implement. Okay, GUU, same story. I'm going to do partial GU, partial U. It looks, all this stuff's mostly the same, so I'll just kind of write this down quickly. If anyone has questions about anything, speak up. B transpose Hessian of V k plus 1, B, and then same kind of stuff on the other side, PK plus 1 transpose con I, commutator matrix, partial B, partial U. And then we get these mixed terms. And I actually don't need to compute both of these. I only need one of them, technically, right? Because they're each other's transpose. So I can write them down. So this is partial GX, partial U. So this is like the mixed partial of the cost. And we're going to get this guy, an A on one side and a B on the other side, and then the same sort of thing in here. And then this ends up being partial A, partial U. And then the last one, we can, again, these are going to be just each other's transpose. So we don't actually have to compute both of them, but I'll write it down just to cover all the bases. So this is UX. Okay, so that's the whole thing. We put a big box around this. Okay, that was a lot. So first questions about this. Hopefully I didn't freak you out with weird weird tensor math too much. Okay, so some notes now. First note, this thing, these tensor terms here, I'm going to put a box around these. So if you've heard of DDP, differential dynamic programming, you've also maybe heard about iterative LQR or ILQR. These are almost the same algorithm. The difference between them is, let's call these tensor terms. Okay, so often the tensor terms are left out. Because they're kind of both expensive to compute and annoying to compute. And going back to stuff we talked about when we were doing Newton's method, basically what happens if I leave those out is I'm doing Gauss Newton instead of full up Newton, right? Okay, and all the kind of comments that we made last time, well, like previously when we talked about Gauss Newton versus full Newton, and how with Gauss Newton, things are guaranteed to be positive semi-definite, and that's kind of nice. Whereas with full Newton, those extra sort of curvature things from the dynamics constraints can make your Hessian indefinite and stuff like that. Still applies here in a major way, actually. So let's see. Let me just write version without tensor terms. Is often called ILQR, iterative LQR. And it's just the Gauss-Newton version of DDP. Okay, so let's see, what's next? Okay, so that's cool. So what we're going to talk about next, a couple things. So first, so we do this whole backward pass. We compute all these things, in particular the D's and the K's. Those are the corrections to our controls. Then we have to do a forward rollout, because that just gave us corrections to the controls, not to the states. So I'll just kind of write this down like pseudocode style. So I'll start with delta J. So this is the change to the cost function, which we're going to do some bookkeeping on. So for K equals 1 to n minus 1, we're going to do U prime, say, K. So our new U is going to be the old U minus alpha times D K minus K times delta X, which is X prime K, i.e. the new X, minus the old X. Okay, let's see. New value, old value, i.e. old iterative of the algorithm, and this alpha is a line search parameter. Okay, so we do that. That's how we compute our new U. Then we plug into the dynamics. So we get X prime K plus 1 equals F of X prime K U prime K. And then I'm going to write this thing down. So this will kind of compute this also in the rollout. And let's. This is GU K, let's say, transpose BK. So does anyone know what that thing is? for, that delta J thing? What did I just do there?
Gradient descent.
That's the expected reduction in the cost using the first order Taylor expansion from the backward pass. So GU is the gradient of the cost with respect to U. And so what I did was multiply that gradient of the cost with respect to U by the step direction, by the step, right, with the alpha on it to do the backtracking. So that's the expected cost change according to the linear approximation. So that's what I need to do a line search. So that's the next thing. So this is what I need to do the Armijo condition, basically. So I start with alpha equals 1. Then I do say x prime, u prime, and delta j. I get these from running the rollout. Given sort of x, u, d, k, and some alpha. Then I do alpha equals c alpha, where c is my sort of chop the step size in half kind of thing. I do this while j evaluated at the new trajectory, the cost function evaluated on the new trajectory is greater than cost function evaluated on the old trajectory. And here, what did I do? This should be, I gotta look at my code now. Did I make a minus sign on how to define this? So I think this has a minus sign on it. This is the way I define this. So this is like a B delta J. Okay, so C and B are line search parameters. So B is the tolerance, Armijo rule tolerance. And this is usually, you know, like 10 to the minus 2 or something like that. And then C is sort of step length reduction or backtracking, I should say. And this is usually like 1/2 or so. So this is just the Armijo rule. It's just how you implement it on top of DDP. So we need the linear approximation, right? Okay, and then you repeat these things. Repeat backward pass, forward pass with line search until convergence. Okay, that was a lot. Questions about this?
When computing delta J, why don't you have a corresponding term? I mean, a term corresponding to GX.
Yeah, so I don't need it, it turns out. So what I did in the backward pass is these GUs, they are the derivative of the cost to go, and in some sense, basically the total cost with respect to the U's. And in the like linear, in the Taylor expansion of like the action value function that I compute in the backward pass, I'm never actually computing X's in there, right? I'm not computing any delta X's. I'm only computing delta U terms. And it turns out all of as far as that Taylor expansion is concerned, all of it's wrapped into the U updates. So those G's sort of are like the total derivative with respect to U, accounting for the linearized dynamics as well. So it turns out that's all you need to compute the linear approximation of the expected cost decrease, according to the Taylor expansions you computed in the backward pass. Does that make sense?
Yep, that makes sense. Thanks.
Okay, cool. So I'm going to switch over and yeah, go ahead.
I also have another question. Is that is it always guaranteed to converge?
Is it always guaranteed to converge? No.
Yeah.
It sort of, has the same exact caveats as like Newton or Gauss-Newton that we talked about at the beginning of the class, where like these are local methods, right?
Yep.
So you need a line search, and in general, you need regularization as well, especially in the full DDP version where you have those tensor terms, because they can make the action value Hessians and or cost to go Hessians indefinite. So you can get increasing, direct search directions instead of decreasing search directions unless you regularize. So all the same stuff happens as before. It's just like a lot of extra machinery here, but you still have to regularize and you still have to line search. And if you do those things, you can prove convergence to a local minimum. So like the closest local minimum to where you started with your initial guess kind of thing.
Okay, thanks.
Yeah, okay, so let's do some fun stuff. Okay, so here is some code implementing everything we just did. So we're gonna do this on the Acrobat. So Acrobat's a fun, like kind of benchmark robotic, under actuated robot that's like really fun to play with controls wise. It's a double pendulum with an actuator at the elbow joint. So only one actuator. And I'll show you video picture animations of this. So here's the dynamics. We're using our robot dynamics toolbox to get those. So I don't have to write them down by hand. RK4, like the same stuff we've been doing, setup stuff. So we've got 4 states, 1 input, 10-second horizon time, and we're doing like 20 Hertz sample rate. Cost functions, these are just random things I wrote down. So basically I put a big terminal cost on here. I should say what we're gonna try to do is, and look at my cost function, I put a goal state in the cost function. So it's just a quadratic cost on X and U with a goal state. So what's happening here is that we're gonna start the Acrobat, the double pendulum, hanging down. And I should show you the picture of it. So here's the Acrobat. It's a 2-link pendulum basically, and there's a motor in this elbow joint, but not at this shoulder joint. So the shoulder joint's totally passive, only the elbow has a motor. So it's under actuated, it's highly nonlinear. It's a double pendulum, right? So it can be chaotic, all this kind of insanity, right? So very nonlinear. But it's kind of nice because it's like a prototypical under actuated nonlinear system that's fun to play with. So what we're gonna do is put a big terminal cost on this and try to get it to swing from the lower passively stable equilibrium up to the standing up position. So that's our cost function, big terminal cost and just some kind of random weights for like the stage costs that don't really matter too much. So there's the cost function, and basically I'm penalizing deviations from that upright goal state. Cost function stuff. Initial guess is random noise. I'm just sampling random U's. So what we're gonna do here is sample a bunch of random U's, then do an initial rollout through the dynamics to get initial X's. Evaluate the initial cost, which is huge because it's not doing anything smart. And then here's my algorithm. So this is what we just talked about, P's, D, K, delta J. I go through the backward pass. I use auto diffing to compute the A and B matrices. Here I've just implemented the ILQR version without the tensor terms. I'll show you the version with the tensor terms next. But yeah, so the same basic stuff. This is the G's expanded out. This is computing the step, computing the updated P's, and then computing this expected cost decrease. And then I do forward rollout with a line search. I roll out the dynamics, I check the cost. I have my Armijo rule in here. And that's kind of it. And I backtrack on alpha until I meet the Armijo condition. Okay, so easy enough, not too complicated. So let's run that bad boy. Takes a second. My code is very slow and bad, by the way. Brian's a much better Julia coder than me. So your homeworks, the reason your homeworks are nice is because Brian cleans up my messy code. So here's the plots. So you can see it does sort of a double pump thing and swings up. The orange line is, which one is this? So the orange line is the elbow joint. The blue line is the shoulder joint. And then here's, oops. Yeah, it's probably easier to just play the animation of it. So let's animate it. Kind of does this like double pump swing up thing and gets to this upright position. So again, yeah, this is super nonlinear, and the algorithm is kind of reasoning about the energetic behavior of this thing, and it's doing something smart to like take advantage of those natural dynamics to swing up. Any questions about this? Okay, so real quick, I have also the full DDP version. And actually one thing to note is the IOQR here with our line search and everything took about 300 iterations to converge, which is kind of a lot. It turns out this is like a kind of a very nonlinear problem. It takes a lot of iterations. I'm just going to quickly, so this is exactly the same, but I implemented all the second derivatives of the dynamics by just nesting the forward diff calls and doing the vectorization stuff that we talked about. And then here's the implementation and what it looks like. So these are those second derivative terms. And here's how they show up. It's exactly like we wrote down in the notes. This com is that commutator matrix. And cool. Okay, so let's run it. So there's something else fun that I wanted to point out. So I saved the initial guess. So let's run this guy. Okay, so this took 188 iterations. So it takes a little bit less on the iteration count than the Gauss-Newton maybe. But the iterations are more expensive. And you have to regularize this one. And you have to actually the regularization is non-trivial with this guy and can be quite complicated. Here's my regularization, by the way. Here's my regularization code. It's sort of weird. This might not make sense to you right now. I might take a little extra talking about that and what that actually means. But basically the takeaway is, yeah, the full DDP can converge in fewer iterations, but the iterations are more expensive and more problematic sometimes because of the need to regularize and stuff. So I would say most practitioners will just use the IOQR version and leave out those extra terms because at the end they're not a huge win. So okay, so here's the plots. I wanted to just show something else cool here. So this I'm using again random noise to initialize this and guess. And like we talked about, it's only ever going to find you a local optimum. So it just so happens that I saved this initial random guess when this came out, so I could show it to you again. It comes out with a different solution. So notice this one has like 3 pumps, and let's animate it and look. And it's a qualitatively different solution. So it sort of landed in a different basin of attraction than the other one. This one popped out about once every 10 tries. So I saved this so I could show you, but see how it sort of swings up and looks qualitatively different. We can compare them if you want. Let's compare the videos real quick so you can see both versions. So this one sort of does a pump and swings right up. This one does a pump, but then kind of like swings up in this folded over position and then swings the top link up at the top. So they come out a little different, and but the costs are interestingly about the same. So this converged to a cost of like 563. This one was, oh, I didn't write it down. $562 and change. So they come out about the same, right? The initial cost, keep in mind, was like 5,000, 6,000, right? So that's pretty good. So they both converge to pretty low cost, like local optima. But they converge to different local optima based on the random noise initial guess that I gave it to start out with. And that's sort of something to keep in mind with these methods. They're local. They're only going to find you the closest local optimum to your start and guess. So in general, you'll get different answers out, and you have to kind of just like be okay with that because there's not really anything else you can do. Okay, questions about this?
What was D again?
D is the feed forward control. So when I compute delta U in the backward pass, I get 2 terms. I get one term that's a constant correction to delta U, and we call that one D, and that's just a feed forward term. And then I get a second term that's some matrix times delta X. That's a feedback term, a state feedback term. So I get these 2 terms, and I need them both to compute the updated U's, or when I do the forward rollout. So I get both of those terms in the backward pass from that Taylor series math that we wrote out. That's just what happens when you have a second order Taylor expansion on everything, right? The feed forward term comes from like the gradient, and the feedback term comes from the Hessian, basically, in the cost to go approximation is more or less what happens. And then when I do the rollout, here's my update on U, right? It's the old U, and then I have the feed forward term that's just added on, right, as a constant with the line search. and then the feedback term, which is k times delta x. And
You-
delta x is the new x minus the old x, right?
Mhm. And you use the feed-forward term to monitor the convergence.
Yeah, so right here, yeah, there's a few things, there's some subtlety there as well. So you can think of the feed for this D, right, is it's the update on U. It's the feed forward update on U. It's basically, it's also related to the gradient of the cost with respect to U. So like when that feed forward term goes to 0, we've converged, right? And so it's a way to monitor convergence. There are other ways. This is just the simplest way. But there are definitely other things you could use to monitor convergence. You could also compute like the actual gradient of the Lagrangian if you wanted to, right? Here, just the same as we could in other methods. Yeah, so you can do all the same stuff we talked about. This is just a cheap and easy way to do it. That's in terms of stuff we already have. Similarly, like in the Armijo condition here, I could have done that, you know, the way we always do it, but it turns out that I can compute that the sort of linear approximate, you know, cost decrease term from Armijo conveniently by recycling stuff that I've already computed in the backward pass. So I do it, right? So that's kind of it. And I went to pretty coarse tolerances here, but this will actually work pretty well to pretty tight tolerances as well. So we can run this, like, for example, I can run it to like 1e-8 if I want to. That's just a handful more iterations. Actually, I'm not sure how well this will do on this problem. It might actually take forever on this problem. Unclear. Maybe that was a bad move. Okay, so we're kind of out of time. There are a few other things I wanted to talk about, like takeaway stuff for this, but I think we'll have to do that next time. So, so yeah, I'll hang out and answer questions, but that's kind of it. I'll post the code. Yeah.
Is
You don't
the
want me to try
feedback,
anything?
is
Yeah,
it,
go ahead.
is it the feedback term in this case still meaningful for something?
Yeah, absolutely. It is. So this was going to be in the notes. The punchline there is the backward pass of this algorithm looks a whole lot like LQR, right? We kind of already hinted that the feedback term comes from the Hessian terms, and the feed forward term comes from the linear terms. And the feed forward term goes to 0 at convergence, right? It's basically saying, oh yeah, you're not updating the U's anymore. Like it means you're there, you're at the optimum, right? There's no more feed forward. But you still, from the Hessian terms, you still get the feedback Ks. And it turns out those feedback Ks at convergence are the LQR tracking gains that you would have gotten from doing a TVLQR backward Riccati recursion with the same cost weights. So if you plug in the same like cost, quadratic cost weights and do a TVLQR backward pass on the answer, you'll get the same gains. So one of the cool things about DEP or ILQR is that it gives you also a tracking controller for free, basically. It gives you, and in fact, if you think about this, there's a lot of insight in here into like why LQR works so well and why this is, you know, actually a good thing. So what we did here is we approximated dynamic programming with like a Newton kind of method and did like second order Taylor expansions to find an optimal trajectory. And it also, it so happens, right, it spits out a local feedback policy as well from the dynamic programming thing. And it turns out what that feedback policy is the local linear approximation to the optimal feedback policy. So if I had done real deal full up dynamic programming where I computed the value function over the entire space and everything, got some super general feedback policy, locally for very small deviations from the nominal, you know, trajectory or whatever, if I did a local like first order Taylor expansion of the optimal policy, this is what I would get. So like in some sense, so this is kind of one of the reasons, like I hope it was clear, you know, in some of the LQR stuff you did. LQR is actually incredibly good. It's really powerful. It works like so amazingly well, like surprisingly well for something so dumb and like simple, seemingly simple, right? Just linear feedback, but works really well. And part of that is that it's actually in this context, right, in this DDP context, it's clear that what it is actually the local approximation of the optimal policy. So if I don't get pushed too hard off my reference trajectory, what I get out of that policy is actually what the optimal policy would give me, right? So for small deviations, small noise, it is the optimal thing. It's actually really good for small deviations and small noise.
Yeah,
Cool.
and in this case, could we like kind of like solve like how we solve the discrete algebra Riccati equation to solve this trajectory planning thing? Like I know here we have some iterative thing that will change, I mean, it's time variant, but Could we still
Yeah,
have
so-
the similar way to do that?
Basically, that's what this is. So like the backward pass of this algorithm is sort of a generalization of the Riccati equation. It's the Riccati equation is buried inside this backward pass. This backward pass has more terms on it than the Riccati equation, but the Riccati equation is in there more or less. So this is sort of, think about this as like a generalization of that Riccati equation from LQR. So this is kind of, yeah, this is the like sort of nonlinear, generalization of that Riccati stuff to like a nonlinear trajectory optimization problem in some sense.
Yep. So in this case, we could only solve it iteratively, right? Instead
That's
of
right,
like
yeah.
some better way, like some closed form to do that. So there's no
Yeah, that's
way to do
exactly.
that.
So yeah, there's no closed form solution for these problems, right? These are nonlinear, non-convex, et cetera. This algorithm is is basically iteratively approximating the nonlinear problem as something like an LQR problem, and then doing something like a Riccati solution, right, to get you an improvement on your guess. So I make a guess, I do this, a bunch of times. I relinearize the dynamics about some reference trajectory, get something that's like LQR-ish to compute an update, right? So that's why it's called iterative LQR. That name's, take it or leave it, but it's not exactly LQR, right? There's a bunch of extra terms in there that are not an LQR. So maybe iterative LQR is not the best name, but that sort of gets at it, right?
Yep.
Okay, so this is kind of the generalization of those Riccati LQR ideas to the nonlinear setting, where it ends up being this iterative approximate thing. That's sort of like a Newton method.
Thanks.
Sure.
Is there any disturbance?
So here, there's not. I didn't simulate this with disturbances. You're going to do that on the next homework. So in particular, right, like I've mentioned, the LQR, the feedback policy that you get out of this at convergence is an LQR controller, and it's the local approximation of the optimal policy. So if I add noise to this thing and run it with the feedback term still in there from this algorithm, I'll get a good tracking controller that will track with disturbances and noise and perform really well as long as the noise is small.
Thank you.
Yep. All right, anybody else?
Did you try to run these two solutions from the same random initialization? I'm just curious of how they would actually differ.
I didn't, they're in separate notebooks and I'm just using random seeds. They mostly come out with that same solution. I just saved the, like, basically one in every, I don't know, 10 trials or something, it comes out with that other answer that looks a little different because the initial guess landed you in a different basin. So I just saved that one to show you, to emphasize that you can get different answers. I didn't run them on the same scene, but the convergence behavior is pretty consistent. Like for example, like I don't know why what this thing's doing. But yeah, I can rerun this and it'll basically always come out with roughly 300 iterations with whatever random seed I give it. So yeah, we can do this again. Which I screwed something up. I might have to restart the kernel. I don't know what I did. But yeah, basically on this problem, like this is a nonlinear problem, but it's pretty benign. It's like low dimensional and this method works really well on it. And so yeah, basically from any random initialization, this will converge in more or less the same number of iterations, give or take, and kind of do the same stuff. That's not generally true, right? So like on harder problems, all bets are off and like you might need to provide a more sophisticated initial guess to get the behavior you want.
I see. Cool.
Yeah. All right. Anybody else? All right, I'll see you guys later.
Zach, one more question. So I assume the next time we will handle constraints in DDP settings.
Probably not. I'll talk about it a little bit, but I don't want to like, I'm probably not going to derive it all. It just gets pretty messy.
Okay.
So if you want to, yeah, so places where you can get that, I think the Altro paper basically talks about that a bunch. There are a few other places to get it. I'm going to like sort of mention it, but not like go into the details in the class.
Okay.